Our first speaker is Rinat Kedem from IUPUI, right? I think. And
no, absolutely not. No. Try again.
She never was at the University of Illinois.
okay.
Thank you. I should have written that there, but it makes a big difference.
No, and she's going to talk about the algebra of creation and annihilation operators for q-Whittaker functions. Whittaker.
Thank you. Yeah, and I'm very sorry I can't be there in person to see everyone. This is my third time missing my visit to Montreal this year, so I really have no excuse, except that it's so far away. Yeah, so first I want to say that I feel really privileged to have known John over the years. I think I met him in the same conference as Michel Gertman, possibly in '98. And John he knows everything, it seems like. He's heard about every possible mathematical question that one can pose to him. And so it's been a privilege to have discussions with him over many years. And also, he's a wonderful conversationalist, as we all know. He knows everything about culture and has deep opinions about politics. So it's been fun. And then I know that, so I thought about what could I tell you? I know John really likes Jacobi 3D type identities, so I thought I'd present some results in that light. And I apologize to those of you who have seen a version of these results before, but maybe the way I present them today will be slightly different, or maybe very likely you didn't understand last time I presented them. So, and this is joint work with Philippe Di Francesco. And I'll start. You see my slides one by one, right? I want to start with some q-difference operators this time. So these are just McDonald operators, the usual McDonald operators for type A. So they're q-difference operators in variables x1 through xn. By gamma, I mean the thing that translates x by q. So gamma I xj is q to the delta I j x j gamma I. So the other way I'm going to refer to this is as a quantum torus. The quantum torus has variables x1 through xn and gamma 1 through gamma n with the obvious q commutation relations. Okay, and then McDonald operators are just something in the functional representation of certain symmetric elements in the double affine Hecke algebra, which I'm going to refer to as the spherical Daha in this talk. So S Daha just stands for things which are symmetric. Then on Daha, not just the spherical Daha, there's a modular group action, SL2Z, and the modular group, it has two generators, tau plus and tau minus, and it's tau plus that I'm interested in. So this is tau minus, and tau plus acts on the functional representations of the spherical Daha by the adjoint action of this element, which is not strictly speaking in the Daha because it's in the completion of the Daha, but I call it Cherednik's Gaussian, and it might look complicated, but it acts very simply by the adjoint action on the quantum torus. And so how does it act on the quantum torus? Can you? Yeah. So obviously, gamma commutes with x because it's just a function of x. And the only thing it doesn't commute with is this q-difference operators, gamma I, but it almost commutes with them. If you compute, it's very easy to see that if you act with gamma inverse on this q-difference operator, it just spits out a factor of xi times q to the 1/2. So because the x's and gammas are canonical coordinates of some quantum torus, this action on the quantum torus it determines the Cherednik Gaussian almost uniquely. There's just the scalar. that you don't know about. So then I'm going to define the tau plus translation acting on the McDonald difference operators. So the adjoint action on the McDonald difference operator is very simple. It commutes with this part. The only thing it doesn't commute with is this part. And so it just spits out an x to the k if I act with the kth iterated action of the Cherednik Gaussian. So this almost looks like a McDonald operator. The only difference is this power xi to the k. And so I'm going to call these generalized McDonald operators, and I'm going to label them dA. A is for how many elements are in this set I, or the degree of the Q difference operator. dA comma k, k is the number of times that I acted with tau plus. And then there's some algebra that's generated by the McDonald operators and their tau plus translated version, plus the elementary symmetric function. This is a subalgebra of the spherical Daha. And in fact, I can complete it to the entire spherical Daha. Here's a schematic diagram of the spherical Daha. So the x and y coordinates here have to do with homologies on the torus when you compare it to an elliptic Hall algebra, but only vaguely. But what I have is on the x-axis, I write down the elementary symmetric functions in x on the right-hand side, and in x inverse on the left-hand side, because x inverse is also in the Daha. And on the vertical axis, I write the McDonald operators, and on the negative vertical axis, I write the McDonald operators in x inverse. And then these dots are just, actually that's enough to generate the spherical Daha, but these dots are just the tau plus translations that I indicated here. So these generalized McDonald operators, for example, the first horizontal line above the x-axis, these are the D1K. So if I write down a generating function of all of these, that's going to be a current in some sort of Drinfeld realization of some quantum affine algebra, which I'll tell you exactly which one. But anyway, these are sort of the generalized McDonald operators form some sort of a subset of this lattice. And what is this algebra? So the whole thing is the spherical Daha of type AN minus 1 affine. And the theorem says that in the limit when n goes to infinity, this spherical Daha is isomorphic to the quantum toroidal algebra of GL1, for those of you who like to play with some quantum toroidal algebras. And inside here, so that the positive half is called the elliptic Hall algebra, which I think is what gave rise to this lattice graph. Okay, so that's just for those of you who like to play with this kind of things. Okay, but what I am interested in is not the spherical Daha. I'm interested in a q-Whittaker limit of this algebra. It's somehow flattens it out. If you think of the Daha as being something on the torus, this is somehow a flattening of the torus in a way which I can't quite tell you exactly what it is. But so this is the algebra that I'm going to call AQ, which it had to do with the title of my talk. And so what I do is I can take the limit of appropriately normalized generalized McDonald operators, and I'm going to call this straight D AK of X. So these are Q difference operators in X, and they're almost the same as the McDonald operators, except that I lost, before I had an XJ here and a T, and I lost those. So they look almost the same. In particular, the coefficient here is a rational function. And here it's exactly the same Q difference action. So I'm often going to refer to this K as a discrete time variable. So these generalized McDonald operators, I want to think of them as a time translated version of the McDonald operators. And then so this, again, this D's and the elementary symmetric functions, the elementary symmetric functions don't have a t going to infinity limit. They don't change in the limit. They just stay what they are. They generate my algebra AQ. So that's the definition of this q-Whittaker limit algebra. And I know what it is. It's a quotient of something called the shifted UQS, quantum affine algebra. It's a quotient as long as n is finite. When n is infinite, it's just the shifted quantum affine algebra, but it looks really strange in this limit. Or there are people that like to call it K-theoretical Coulomb branch, those people that work on quiver representations and supersymmetric gauge theories and so on. So this algebra is not new. It has some other contexts in which it shows up. Okay, let me go back to the non-q-Whittaker limit and say that in the McDonald theory, in the Daha, there's a lot of symmetry. And in particular, there's an involution which is responsible for something called McDonald duality, or some people call it bispectral property. And it allows you to get Peary rules from McDonald eigenvalue equations. So here is a McDonald eigenvalue equation. So there's some power of t here, which magically cancels out when you take the limit, so don't ignore it. But anyway, d acting on the McDonald eigenfunction is an elementary symmetric function times this function. The elementary symmetric function is not in x, it's in some variable which is related to lambda, which we usually think of as an integer partition. So Si is t to the n minus I times q to the lambda I. Very often I'll use the variables lambda I, which is q to the lambda I also, because lambda I always appears like that. So this elementary symmetric function here, it depends the variables depend explicitly on t, which I have to take into account when I take the q-Whittaker limit. So, but what I'm going to do is I'm going to pretend that lambda is not an integer partition. Lambda is just a formal variable, and I'm going to elevate s to the status of a formal variable, just like x. And I'm going to write p of x and x, p of x and s. Then this eigenvalue equation just takes this form, which right now it looks exactly the same. And once I choose a normalization, and once I choose where I want to expand my rational functions in my q-difference operators, this has a unique solution. So I pick a form for a series expansion. This has a unique solution up to normalization. And the normalization can depend on S because D doesn't act on S. And then if I pick the appropriate normalization, then I can write McDonald's duality in a very simple way. McDonald's duality, for those of you who play with Daha, has to do with exchanging x and y variables. It just says that p of x and s is equal to p of s and x with the appropriate normalization. I call the solution to this equation the universal solution because, in fact, you can get any McDonald polynomial by specialization of this solution. You specialize the variables s and you normalize appropriately. And so if I use this duality property and I just rename the variables in this expression, I get an equation which is, instead of a difference operator in x, I have a difference operator in s. Remember, s is related to lambda, so this is a difference operator in lambda. Acting on my universal function is e, and now e is, instead of a function of s, e becomes a function of x. Okay, just elementary symmetric function of x acting on the universal function. And this is known as the Peary rule. When you multiply a McDonald polynomial by an elementary symmetric function, what linear combination of McDonald polynomials do you get? That's what this difference operator tells you.
Rinat, can you hear me?
Yes. Yes.
Is there a suppressed index to the p, or this is just some kind of universal p which doesn't depend on lambda?
So yeah, so what I did is I exchanged this index lambda for this variable s.
Right.
It's just a notational difference.
Yes.
Right? But then I elevate this to a formal variable. So this was an index. This is now a formal variable.
Right.
So I can act on lambda by shifting lambda, and that's what I'm doing here.
But I mean,
So I can now rewrite this in terms of lambda.
Usual, but the EAs are just usual elementary symmetrical.
Yes. So I never do anything with my elementary symmetric
They don't
functions.
depend
These
on,
are just,
they don't depend on
Yeah.
Q.
Yeah.
Sure.
yeah, they don't depend on Q, they don't depend on T.
But the usual theory rule tells you that's the sum over various young diagrams and so on.
Yeah, it's shifted with some coefficients, and that's precisely what this will tell you.
So this McDonald operator is doing the same thing as providing a linear combination of.
Yeah, with modulo some things that I'm hiding under the rug, which has to do with conjugation by some lambda, some power of lambda. But yes, basically the McDonald operator modified a little bit is the Peary operator.
So is there some diagrammatic way to express that in terms of young diagrams? The way they usually.
I'm sure there is. But you have to specialize lambda now to be an integer partition. So once I take this equation and I specialize lambda to be an integer partition, then yes. So yes, so what should I say? I think one should view E, yeah, I think one should view E as a vertical strip, right?
Yeah.
And so then what you do is you play around with the boxes, right?
Yeah, so maybe it's the same diagrams but with different coefficients. I mean, with the usual theory rule, you just have.
This is the usual Peary rule. I just want to say that you can derive the usual Peary rule from the eigenvalue equation. I'm not saying anything new. McDonald knew this fact, but he just didn't write it in terms of these formal variables. He wrote it in terms of partition.
The usual theory rule for Schur functions or for
No, for McDonald polynomials. For McDonald polynomials. Yeah, what I want to say is that this is a Q difference operator in lambda. So what I have is I have lambda, sorry. It's a Q difference operator in lambda I, which is Q to the lambda I. And the Q difference operator, I'm going to write TI. So now I'm going to have a second quantum torus, which is made out of lambda I and TIs. So TI is the thing that multiplies lambda I by Q. Yeah, and I'll give you, yeah, maybe you'll see a little bit better how precisely it acts. But for now, it's just, it's in fact a rational operator, this thing. So it's not very beautiful, so I'm not writing it out. Let's see what happens to the eigenvalue equations when I take the q-Whittaker limit. And the answer is, okay, nothing happens. Again, I said this before, nothing happens to the McDonald or the generalized McDonald operator. I just lose this minus xj here and the t here. So the left-hand side of the eigenvalue equation is just as ugly as it is in the McDonald eigenvalue equation. But the right-hand side, something remarkable happens to it, because E of s, which is the eigenvalue in the t going to infinity limit, has a dominant term, which is just the leading power. So, you know, in these variables, so this is the leading power in t. It's q to the lambda 1 plus dot 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 plus lambda a, or sometimes I write this lambda 1 lambda a, or I can write this lambda to the omega a being the fundamental weight of GLN. So the eigenvalue equation is simpler on the right-hand side in the q-Whittaker limit. So I have straight D acting on pi, and now pi is the q-Whittaker limit of the McDonald polynomial or McDonald function. So it's I can say it's a q-Whittaker universal function is equal to just this monomial in lambda times pi. So the eigenvalues are simpler in the q-Whittaker limit. And let's see what exactly, maybe this will help you, John. What happens to the Peary rules? So the Peary rules, nothing happens to the right-hand side of the equation because the elementary symmetric functions, as you notice, they don't depend on t. But the Peary operator is no longer a rational function. It becomes a Laurent polynomial. The coefficients of the difference operator ti, this is the difference operator in lambda I, are just Laurent polynomials in lambda I. So I can write this as lambda I over lambda I minus 1 minus this times ti. So it's much, much simpler than the O'Donnell-Peary operator. And in fact, it's a relativistic quantum Toda Hamiltonian in the variables q to the lambda, not x. So it acts on lambda, not x. This is a function of lambda and x, and this acts on lambda. So I can view this as a Toda type equation, uniquely determines the eigenfunction once you pick a normalization. The normalization, of course, can depend on x because h, which is a q difference operator in lambda, doesn't see x.
Could you just recall the A is a multi-index, right?
No. So
A is the,
yeah.
is the length of I, sorry, okay.
Yeah, it's the degree of q, so it's how many x's or lambdas you take q difference operator. So it's the degree of the difference operator.
So it's just the non-negative.
So A goes from 1, strictly speaking, up to n. The nth one is trivial.
And these are
So
commuting.
These are commuting Hamiltonians. Was that your question?
Yes. That would
Yeah.
be.
Yeah. So just one caveat here. If you know about q-Whittaker functions, they have some highest weight that corresponds to them. And the highest weight, it's not lambda. Even though lambda looks like a highest weight, it's not. Lambda is the variable. The highest weight is parameterized by x because this is acting on lambda. And so if you write xi is q to the mu I, then mu has to do with the highest weight, with the module in which you're computing the q-Whittaker function m. So that's what happens to the Peary rule in the q-Whittaker limit. Okay, so this is just to summarize, those are the two equations I have. This is the eigenvalue equation. The right-hand side is simple. And this is the Peary rule. And here I claim that the Hamiltonian is simple. I put E of x on the left-hand side here. And the right-hand side is a function of lambda. The left-hand side is a function of x. So it can be thought of as a q difference operator in x. So I wrote the words Fourier transform here. I know there's in some sense, q-Whittaker functions form a complete set. So instead of doing analysis, I can just say that if I have a q difference operator in x acting on pi, then however it acts on it, that's the Fourier transform in Cherednik's language of this operator. So I call d hat of lambda this eigenvalue. And I call E hat, okay, in some language of lambda, that's this Peary operator, the Toda Hamiltonian. So therefore, they're dual pictures, the x and lambda pictures.
So in summary, the q-Whittaker functions are a limit of the O'Donnell function.
Yeah, it's well known that this is well known.
Right, and as functions of two sets of variables,
but
partition. So
no, so usually, yeah. Usually one of them is considered a parameter and the other one is considered variables.
right.
And so for the q-Whittaker function here, x is the parameters and lambda is the variable.
Right.
Unlike the.
And these are eigenfunctions of some kind of quantum or little or something. I'm not sure what this is. What was the system? Which integral was
I
this?
can't.
Which
Yeah, I'll
integral?
talk about that. So the integrables, there are many integrable systems here. But one of them are these Toda Hamiltonians, relativistic quantum Toda Hamiltonians. And so far, that's the only one I mentioned. The fact that I have these commuting Hamiltonians. So I just want to say, okay, what about raising operators? So below, I will prove a theorem. There are all these noises coming from everywhere. I will prove a theorem that the generalized McDonald operators, at least the first generalized McDonald operators, the one-time translated, Q commutes with the McDonald operator in this way. So this is actually the matrix min AB. So they Q commute, and equal time generalized McDonald operators commute with each other. And therefore, if I take the McDonald polynomial 1, the simplest McDonald polynomial, and I act on it with a product of dA1s to some power, then if I act on this with a McDonald operator, I'm just going to get some power of Q times the same function. And that power of Q will tell me which q-Whittaker function I have. So if I act on this with dB, I just compute according to this commutation relation, and I see that lambda, what I wrote here, lambda, actually has to do with which McDonald polynomial this is the limit of. So it's the limit of p lambda of x. It's the q-Whittaker function corresponding to lambda. But it's a polynomial, so it's a class 1 q-Whittaker polynomial up to some normalization. The other thing I should say is that we recognized this early on. This q commutation relation shows that these are creation operators or raising operators. So what they do is dB1 adds a column of length b. Okay, so it's like multiplying by the bth elementary, the bth fundamental representation. These are limits of the same thing in the McDonald theory found by Kirillov and Naomi. They had McDonald raising operators, so the full thing. How do you add one column to the partition of a McDonald operator? Well, it's a very complicated operator, but when t goes to infinity, it has this very simple limit, which is what I call the generalized McDonald operator. Okay, so I want to talk a little bit about this algebra of raising and lowing operators and the generalization to other root systems, because everything I've said so far is about type A. Okay, so here's another integrable system you might be familiar with. So this is for SLN. You write down a transfer matrix. You have an auxiliary space and a bunch of quantum spaces. And for the auxiliary space, I'm going to pick a finite dimensional representation. I don't mind if it's the Yangian or the quantum affine algebra, which has a particularly simple form. It's isomorphic as a D module to a highest weight module with rectangular highest weight. It has a spectral parameter, and I require, so if I fix zeta, I take a family of transfer matrices with zetas shifted by integer powers of Q. So this is some combinatorial data for this transfer matrix. I haven't said so far anything about the quantum spaces, but it's well known that whatever you choose for the quantum spaces, these, because of the R matrix form, for either the Yangian or the quantum affine algebra, they satisfy fusion relations. So if you take this set Tijk, so I is the dinking label, K is this the width of the Yang diagram here, and I is the height of the Yang diagram here. These, among themselves, satisfy a set of different recursion relations called fusion relation or T system, and it looks like this. So it's just a it looks completely combinatorial when I write it this way. So here, I goes from 1 to n, and j and k are integers. And this has the form of discrete Hirota equation. This was recognized by Lipan and company And so they said, okay, these T's are, these transfer matrices are discrete tau functions. And I should mention that in the modern literature, this is not, this is considered to be an equation for Q characters in the language of Frankel-Rashetikan, in which case you completely ignore what you have here as quantum spaces, and this is just an equation for Q characters. But I should say that a couple of months ago, we came across another incarnation of this equation. So it's a very popular equation. I think you see it everywhere. And I think the spectral curve community in supersymmetric gauge theory crowd, they call these now QQ systems, which is incredibly confusing, as you will see in a second. But if you happen to have run across that language, we believe it's the same as these T systems.
They're also Pluto relations.
Yeah,
Sure.
yeah. Well, I'll get to that. Just wait. Of course, I have to talk about that. Okay, so the classical Q systems are just the limit of these fusion relations, where you ignore the spectral parameter. So if the T system is an equation for Q characters, once you forget the spectral parameter, these are just equations for characters of finite dimensional modules of SLN in this case. And as you observe, these are Plucker relations. And of what matrices? So if you take the discrete Wronskian matrix, so I just take Q with Dynkin index 1 sub K in the upper left-hand corner here. And then I increase K to the right and decrease it down, and I write down this discrete Wronskian matrix. Then from the Jananu-Jacobi relation, which is this relation, I think you've seen it already recently, so I don't have to explain it. If I choose Q0, Q at time 0 to be 1, which has to do with the fact that the character of the trivial representation is 1, then QIK is the determinant of the I by I discrete Wronskian matrix from this relation, from the Denano-Jacobi relation. And to get even closer to your favorite identity, so we know that characters satisfy this relation. So remember that the character of the first fundamental, so the symmetric power representations, those are just the complete symmetric functions. So if in the discrete Wronskian, I just plug in the complete symmetric functions, and this is a special case of the Jacobi-Trudy relation. This is indeed the character of the KR module corresponding. So this is, I think, KR K omega I. You can call it that. So that's these Qs with this special initial data. But also this Q system has a Poisson structure, because I know that the Q system variables, so QIK, are A-type cluster variables in a cluster algebra with the following quiver. If you like to play with quivers, or exchange matrix, which is Q symmetric. Here C is the Cartan matrix of SLN. It's non-degenerate. This matrix is invertible. So therefore, these variables have canonical Poisson structure. They have canonical, log-canonical commutation relations determined by essentially the inverse of this matrix. And so the integrability, so this tau plus, which generates for me time translations in K, says that this translation, this time translation, discrete time translation, has conserved quantities which are invariant under tau plus. And those are the classical limit of the quantum total Hamiltonians that I wrote down before. That's my claim. So in fact, I won't show that. I will just show that for the quantum, for already the quantized version. So if you have a Poisson structure, you can quantize it. So you do the canonical. So I forgot to say, okay, I think that Misha German told you about all of this a couple of days ago, so I don't have to say any of this, right? Where it comes from. So I was just trying to remind you. Okay, so we have a canonical quantization, and this is what it looks like in type A. So in type A, you possibly forgot what the Q system looks like, but it looks like this, except that the Qs don't have hats on them. Those hats are what makes it quantum, those hats and the fact that I have a factor of Q here. This is just equal to I, in fact. But also, these are now non-commuting variables, and so it's because I wrote it in this order that it looks like this. There's an order to the multiplication. In fact, these commute among themselves, these commute among themselves, and these two don't commute among themselves. Was there a question? So how do they not commute among themselves? This is how they don't commute. If you take at time k and time k plus 1, then they q commute. And they q commute according to this matrix, which is essentially the inverse Cartan matrix. This is min ij. At equal time, they do, sorry, there's something missing here. Isn't epsilon missing here? So it's equal, if epsilon is equal to 0, then actually these commute. They don't commute at neighboring times. And if you have a difference in time 2, then you have to use what I call the quantum Q system. And here's the theorem. So this is some sort of algebra. It's a non-commutative. They generate some non-commutative algebra of which these are the relations. And the theorem is that my generalized McDonald operators in the q-Whittaker limit are the functional representation of these elements in the Q system algebra. So that is the algebra generated by the solutions to the quantum Q systems is this shifted quantum group. Okay, so that was for type A, and now we observe that there is a quantum Q system. Well, no, sorry, there is a Q system for each affine root system. So this goes back to, I think, the late 80s. It goes back to thermodynamic beta ansatz, where this comes up as a in the completeness question, or in writing down the order 1 excitations in the thermodynamic limit. So these Q systems were written down by Kirov, Shetikin, and then Kuniba, Nakanishi, Suzuki, and a bunch of various Japanese groups. They wrote down all of these Q systems. So here it is for type D, affine D, type N. And so I just want to give you the general structure. So again, this is descended from some T system. So it's an exchange relation between Q, K plus 1, Q, K minus 1 on the index, the Dynking index I. So this is I, right? And the only difference between all of these Dynking indexes is what happens to this monomial term here. This is the only thing that changes. This part is the same for every equation, and the monomial part depends on the neighbors in the Dynking diagram. So here, for example, these are the 2 neighbors. And here, you're looking at this node, it has 3 neighbors, so this is a cubic term. And this node only has 1 neighbor, so it's there by itself. Okay, so the claim is that you can write down a Q system for all Dynking types, and the theorem is that they're all integrable, discrete integrable systems. Well, how do I know that? Almost every Q system has a canonical Poisson structure, all except for one particular troublesome one. And so, for example, they're all, apart from this star, they're all A-type variables in some cluster algebra. So I wrote down here the quiver associated to type Dn. What you can see here is the skeleton of the D-type Dynking diagram. And so these B matrices, they're all invertible, so you can write down a canonical Poisson structure, and you can write down a canonical quantization. But so you can write down the quantum Q system for each type, but I want to emphasize that now the variables Q hat So they're not characters anymore. They're not Schur functions. And they're not quantum Schur functions. They're operators, which have the interpretation that they're raising something like a generalized q-Whittaker function. They're raising it to a q-Whittaker function with this weight, which has this k omega I added to it in some way. So they're q-difference operators. They act as creation and annihilation operators. And what are these generalized q-Whittaker functions? Well, I like to think of them as linearized partition functions for the spin chain, but I'll get to that at the end. Okay, so that's the general idea. And so how do we find conserved quantities for each of the Q systems or the quantum Q systems? So for the classical type, ABC, sorry, BCD, there are there's Kornwinder theory, there's a spherical Daha, and Kornwinder plus Van Diezen and Rains and us and MacDonald wrote down generalizations of the MacDonald operators, of which you have to take judiciously selected linear combinations to have anything to do with our Q systems. But it's possible. This is what we did. And Kornwinder depends on some parameters A, B, C, D, which you specialize them to get affine root systems. And these are the affine root systems you can get. So you have affine B, affine C, and affine D, and then you have some twisted ones. And so you specialize these parameters A, B, C, D, and the specialization, it depends on T. The q-Whittaker limit, remember, is when T goes to infinity. So when T goes to infinity, so once you've taken the specialization, you can take the T going to infinity limit of your q-difference operators that depend on the root system. Before you take this limit, you have, again, MacDonald duality. This is due to Van Diezen and the theorem of Sahi and so on. You have the MacDonald type duality also in this case. And so you can use this duality to get from the Kornwinder operators the quantum total Hamiltonians in the q-Whittaker limit. So these will then be, so the same procedures that I showed before will give you quantum total Hamiltonians. They have boundary terms that depend on the root system. The theorem is the following. The q-difference operators you get as a result of taking the q-Whittaker limit of the specialized Van Diezen Kornwinder operators. And then you take the tau plus translation of those. They satisfy quantum Q systems for the appropriate affine root system. There are many, many subtleties in this that I'm hiding, but this is the general idea. And so therefore, you have an algebra of raising and lowering operators for these generalized q-Whittaker functions for these other root systems. And in maybe I have 5 minutes to say something about the ingredients of the proof. So there's this Fourier transform trick, which is very useful. Usually that involves a lot of analysis called Whittaker transforms, q-Whittaker transforms, b-Whittaker transforms, and so on. And I'm not an analysis person. I do it a very simple way. I say, okay, I know that q-Whittaker functions are in some sense complete. So if I have some q-difference operators in X acting on my functions, on my universal function, as a q-difference operator in lambda, and if I know that these theta I of lambda satisfy relations R with the opposite multiplication, then I know that the q-difference operators in X satisfy R with a right multiplication. So if I can prove that these operators satisfy some algebra, then I know which algebra these operators satisfy. And the key is the following. You start with a eigenvalue equation. Okay, so in the q-Whittaker limit of the Kornwinder eigenvalue equation. And so you have some Kornwender operator on the left-hand side acting on the universal q-Whittaker function by a monomial lambda to the omega star. Okay, I didn't say what omega star is. Omega star is omega, except in one case. Let me show you these graphs again. Yeah. You see this? These two root systems are exchanged under the star operation. But if you're not worried about non-simply laced cases, don't worry about it. Yes. So the right-hand side here is really simple. It's just a monomial. And so the Fourier transform of the Kornwender operator is really simple. It's just a monomial. So what I'm going to say is I'm going to find a set of q-difference operators in lambda, which are solutions of the opposite quantum Q system. So I have an opposite quantum Q system from the cluster algebra. And these are their relations. I wrote them before. So I have exchange relations in particular, which depends on omega star and omega. And this monomial, as I explained, it depends on the particular form of the Dynking diagram, but the rest of the terms don't, except for this power. So this is always the form of the quantum Q system. I take this for each G and I compute a unique up to scalar multiple element G lambda, which depends on the root system, which performs the following function. When I act on it on D hat, so these are functions of lambda, remember. When I act by the adjoint action of G, which is a q-difference operator in lambda, I get the translated q-difference operator again in lambda, and most of the time it's translated just by one, except if I have short roots, in which case it's translated by 2 time steps, and then I have to do something. And I can do this, I can compute this. The fact that it exists is not trivial, it's by computation, it exists. Not only does it exist, you can compute it explicitly from this quantum Q system. And not only that, once you do compute it, and you've already computed the quantum total Hamiltonians, you will find that miraculously, G, the time translation, commutes with the Hamiltonian, with all the Hamiltonians. So here's another bit of integrable system. This is a remark on Baxter operators. Why should G commute with the Hamiltonians? So this is why we think G commutes with the Hamiltonians. It's true at least in some types, possibly true in all types. This operator is an evaluation at spectral parameter equal to 1 of the Baxter operator of a very special form. So the Baxter Q operator can be expressed as a product of quantum dilogarithms in some infinite system, okay? It's a sequence of mutations in some extended cluster algebra. In type A, you can take this extended cluster algebra, the spectral parameter sits here. And this is something that you can look at in Schrader and Shapiro, they write this down. In type D, if you start like this and you follow a certain rule, you'll find Baxter Q operator. You can do this in type B, you can do this in type C. In any case, it'll give you a sequence of mutations in a quantum cluster algebra is a product of quantum dilogarithms. That is the Baxter Q operator. It depends on the spectral parameter U. You evaluate it at Q goes to, and at U goes to 1. You get a product of something, and I claim it's G. G is a product of quantum dilogarithms. You have to use identities on quantum dilogarithms to show this. So in that sense, the Baxter Q operator, it's a generating function for conserved quantities for these Hamiltonians, but it's an exponential generating function, you know, as distinct from the characteristic polynomial that you write down for the Lax matrix, which is a polynomial generating function. The Baxter Q operator is an exponential generating function for total Hamiltonians. Let's see, I'm almost out of time, so I'll finish up. And then you have to prove a theorem that says that, in fact, this G is the Fourier transform of the Cherednik. Remember Cherednik's Gaussian from the beginning of this talk? Maybe you don't. Gamma of x is exp sum log xi squared over 2 log q. I claim that the Baxter q operator is the Fourier I claim that the g function, the function g, is the Fourier transform of the Cherednik Gaussian. That is, when acting on the universal q-Whittaker function, gamma and g acts the same way. And the proof is just because g commutes with h, if I act on the Pierre rule, h on the universal Whittaker function is equal to e times the universal Whittaker function. Because g commutes with h, I can take g inside, and because g doesn't act on x, I can take g inside here, and I get this equality. And then I say, oh, but the Pierre rules, they determine the q-Whittaker function uniquely up to scalar multiple depending on x, because h acts on lambda and not on x. And I compute the scalar multiple, and it is the Gaussian. That's the proof of this statement. Therefore, as a corollary, I get that, I hope I wrote this down. The tau plus translated q difference operators, that is, tau plus is you act by the Cherednik Gaussian on the Kornwinder operators. They're the raising operators for these generalized now q-Whittaker functions. So if you act with an ordered product of these d's on the eigenfunction 1 up to some factor of q, you get a generating function. So these are just the short polynomials, the characters of the irreducible representations of some finite dimensional algebra G. And these q multiplicities, they're known functions, explicitly known for all these affine root systems. They are associated with linearized partition functions for generalized XXX spin chains, or graded counting of this space of homomorphisms. So the grading comes from the grading operator in the quantum affine algebra. So I've talked about this before several times. I just want to emphasize that this grading, for some reason which we don't understand, comes from the quantization of the Q systems that comes from their cluster algebra structure. So finally, I'll just say, what are we working on now? So there are lax matrix presentations for all of these things, and I claim that you can get them, at least in some cases, from the quiver for the corresponding cluster algebra. And what are we doing with these extended quivers? So they give us some sort of cluster algebra structure for this spherical double affine Hecke algebra. So this is ongoing work with Schrader and Shapiro and DiFrancesco. And the most important thing is, thank you, John, for all of your interesting comments and your attention. And hope to see you soon sometime.
I hope so too.
Thank you, Rinat. Are there questions from the audience? Is there one in the back? The second, you back the microphone.
Thank you for the very nice talk. So you showed that the quiver for A affine and D affine. Is the quiver known for all A, B, C, D,
Yes.
E?
Yeah. No,
Also
it's known
exceptional.
for everything. So yeah, it's known for all. So first of all, I should say that the Q system is associated with an affine root system. To specify an affine root system, you have to specify two finite root systems in the language of McDonald.
Mm-hmm.
But yes, they are all cluster algebras except for the following: A to N 2. We deal with this case. We can nevertheless deal with this case from the Kornwinder point of view, but the quantization is somewhat ad hoc, and we're not sure exactly where it comes from. It's not a cluster algebra.
Okay.
It's a folding of a cluster algebra. But yeah, so the exchange matrix in general has this form. In the non-twisted cases, it's like this, where C has to do with the obvious finite dimensional algebra associated with the untwisted cases. In the twisted cases, it's like this, so it's q-symmetrizable, where C is, okay, depending on which twisted case you're talking about.
Can someone move the picture, the video? It's right on the formula.
Yeah, your video can. I don't know.
Yeah, but that's,
Can you move the video?
Sir. Yeah.
Okay. Yes. Sorry, your video feed was right on the formula that you just wrote. So
I just moved my formula.
no, it's good now.
Good now?
It's good. And what about elliptic? Is there also something, some cluster structure in the elliptic case?
I raised my hand. Fine. So
Okay.
no, look. So I'm not claiming. Oh yeah. We don't know.
Okay. Okay.
Yeah. So here's one statement. The McDonald operators, they're not cluster variables. They're elements in the upper cluster algebra. So already it's not as nice as you would want this to be,
Mhm.
right? When at finite t. Yeah.
And another question, if I may, you mentioned this Baxter operator that was a product of quantum dilogarithms. Could you be a bit more explicit, like about the form? Like, is it a finite product, infinite product?
It's a finite product. No, it's a finite product of q dilogarithms. Let's see if I can. I'm going to go against the arrows. So you mutate here, then you mutate here, then you mutate here, then you mutate here.
Ah,
And then you have to repeat the process.
okay.
It's a game you can play on the app.
Okay.
There's a rule for how to mutate. But actually, this one was written in Schrader and Shapiro explicitly how to do this. It's much easier if I show you by hand how to do it than to read what they wrote. But in fact, and also they had an extra thing here, but you don't need it for what I'm doing.
Okay. Thank you.
All right. Other questions?
Hi, Rinat. Quick questions about this cluster structure you were talking about. Well, working with Gus and Sasha. This is in Philippe. It's a quantum cluster structure, correct?
Quantum.
Yeah, but if you look at the corresponding classical, is there a nice geometric model for that? Like this is a space of function on something reasonable, like for usual, for usual ANQ system, we know that, but yeah.
So we're only doing AN with so they're not hoping to get anything out of it. So this other type is these other types are an obsession of Philippe and mine.
Ah, okay.
So the fact that I'm telling you that there are results that are similar for these other types, I'd be very happy for your help if you could help translate this to the geometric picture in the classical case.
Okay. All right. Thank you.
Okay. Are there other questions from audience or from online audience? If not, oh, John, you have a question? No. Okay, sorry. All right. Okay, let's thank Rinat again for the attention.
Okay, thank you, and great to see you all.